Dobrý den, dámy a pánové. Hello, good afternoon, ladies and gentlemen. Today's lecture will be in English because our guest is from Ukraine. He's originated from the Institute of Physics at Kiev, but then he had to move out from the country and is now localized in Czech Republic at IOCB. But he's also co-founder and I think CTO. She's chief scientific of CSO, then CSO of the London-based startup company Receptor.AI. And as the AI is currently running through all of the newspapers, you will learn from this lecture about how this can be used in a startup company measures. So, Semen, it's up to you.
Yep. Thank you very much, Kyle. I think this microphone works. So basically today we'll try to tell you about AI models which are intended to replace molecular docking in drug discovery. But before going there, we should understand what is molecular docking and what is conventional docking. And then we will go to the AI one and discuss how it differs. Yes, it seems to work. It should. Okay, so it should be closer. I'm afraid I will eat it if I will make it even closer, but yeah, I hope it works. So can you hear it? Okay. Yeah, so basically coming to conventional docking, the definition of docking is quite vague, I would say. So it's a computational technique which is used to predict how one molecule binds to the other. It's as simple as this. And the bigger molecule we call the receptor, the smaller one we call the ligand. And the whole idea is to get the matching like a key in the lock and to provide the optimal spatial arrangement, so-called pose, of the one partner molecule corresponding to the other. And in order to get this optimal pose, we are minimizing something which we call the interaction energy. But instead of the real energy, we are working with some approximated scoring function because the whole idea is to make it quick. So we are not using anything fancy like quantum mechanics. We are using something very simple and very, well, stupidly fast, I would say, to quickly get the optimal pose of one molecule relative to the other. There are different types of docking. The simplest one is protein-ligand docking, when you have the target, which is typically a protein, and you have the small molecule, which is typical small molecule chemistry, and you are getting this molecule in the binding pocket of the protein. From the other hand, you can have the protein-protein docking, which is shown here when you have two large proteins, and you're finding the protein-protein interface, how these two globules are actually coming together. And somewhere in between, you can have the protein-peptide docking, when the peptide is smaller than the whole protein, but larger than the small molecule. So you have something in the middle, and this is actually the most challenging, because the techniques for the small molecules doesn't work, and the techniques for the larger proteins doesn't work either. You can also have protein-nucleic docking when you have your partner, which is not a protein, but DNA or RNA. This is not so common, but sometimes this happens. And in addition to this classification, you can also classify by the rigidity of your larger molecule, your receptor. The docking could be rigid or flexible. So the idea is that your ligand is always flexible. So you can change, you can rotate the bonds in your molecule, you can adjust its conformation. But for the target, for the receptor, it can be either rigid, which is true in most of the cases, or it could be flexible, at least in the binding pocket around your ligand. And also you can do docking in the predefined binding pocket where you already know a kind of cavity where your ligand is located, or you can do it blindly when you know nothing and you are trying to find this pocket on the fly in the course of docking. Then you need something, some function to optimize the energy, to find which conformation is really the lowest energy one. And for this, you can use a bunch of different scoring functions. As I said already, the scoring function is not a real energy, it's some approximation to the real binding energy. And the level of this approximation depends on how fast you can be and what are the assumptions under this scoring function. The most common one is a force field-based scoring function. So you have the classical interaction force fields, which typically expressed like this here. So you have the terms for bonded interactions, like the covalent bond, bonded angles, and their hetero angles inside the molecule. And you have non-bonded interactions, which is typically van der Waals interactions between different molecules, and the electrostatics, which is actually shown here. Sometimes you're also including solvation terms, because as I said, you want to be fast, so you cannot include the explicit solvent. So you are doing some implicit water, either generalized Born approximation or Poisson-Born approximation, which is kind of solving the continuous equation for interacting with water. Another kind of potential are empirical potential, when you have the sum of different terms with coefficients which are determined by fitting to experimental data directly. So you may have, let's say, the hydrogen bonding terms, or hydration terms, or rotational terms, with the coefficients which are really fitted to what you get from experiments. And the next one is a knowledge-based potential. This one is more interesting because what we are doing here, you are measuring the statistical probability of certain pairs of atoms to be at a certain distance. Imagine that you have an oxygen in the ligand and the hydrogen in the protein, and you have a lot of structures, let's say in the PDB data bank. So you measure these distances, and you are getting the distribution, G over R, where R is the distance between these atoms. And after that, if you get the logarithm of this, you are getting kind of energy distribution for this pair of atoms. And after that, you can put it into your force field and to the scoring function. This was the first type of the potential, which is based on the data, not on the physics. And nowadays, you also have the descriptor-based potentials, which are already coming from the fancy machine learning domain. I will not speak too much about this. The idea is that you are using the pool of chemical descriptors related to interactions in your system, and you are using machine learning to build the model which has the weights to minimize the energy function. So all these are actually components of the conventional docking. Even if your docking scoring function is based on the ML, you are still working in the domain of the conventional docking. There are several programs, commercially or freely available, where you can use for docking. As you can see, it's kind of dozens of them, which are more or less widespread. And the most used one is Autodoc, which is free and open source. Then you have Gold and Glide, which are commercial programs and which are used in the commercial drug discovery most. And then you have some else. As you can see, the market share of these is quite uneven. Some of them are very widespread, some of them are kind of niche programs. But the point is that all these programs are quite old. And this gives us the next slide. So what is actually wrong with this physics-based docking? Why we should invent something new? Why we should go to AI, actually? And the first thing is that this field is kind of stagnating. So all the major programs for docking are more than 20 years old. They are developed sometimes in the 80s even. And there are no major improvement in this field for about 25 years. So now we have these ML potentials, which were pretended to be kind of revolutionary, but they don't. So they're not as revolutionary as advertised. And this is the only innovation which we had in the last 25 years, I would say, in this domain. Another thing which is bad about physics-based docking is that it's kind of stretched between speed and accuracy. As I said, docking is designed to be fast, and it means that the scoring function have to be simple. So you cannot do it very complicated, you cannot include anything which involves some very intensive computations, and because of this you are missing some important terms like interaction with explicit water. And also, if you want to do, let's say, covalent docking, when your compound covalently interacts with a protein, it becomes extremely slow because of these constraints. In addition to all this, the docking is not exact. So when you are doing the docking, the search for this best docking pose is kind of probabilistic. So you are getting the kind of minimal confirmation, but this most likely a local minimum. So you have no guarantee that this pose is the best. And the longer you run it, the more probable that you will get something even better than you currently have. So again, you have a kind of tug of war between speed and accuracy. This is not the major problem. The major problem is low discriminative power. So it comes in 3 different flavors, I would say. First of all, you may have the same compound which binds in different poses to the same protein, let's say like this, and the docking score would be identical in both situations, so you have no way to discriminate between these. Then you may have multiple compounds. They bind to the same protein, again with no difference in score. So you cannot rank them. You cannot say that compound A is better than compound B. And finally, compounds may bind to different places on the protein surface, especially if you are doing blind docking. So in a way, you cannot find where the binding pocket is located if you don't know this from some biological data. Sometimes you can, sometimes you not. So overall, docking is kind of bad technique, but there is no alternative with the same throughput. So this is the only technique which you can use if you need to find the binding of the millions of compounds. And it was like this until recently, and recently the AI docking emerged. So what is the difference between AI docking and conventional or physics-based docking? Again, as I said, in physics-based docking, you can have kind of algorithmic search for the energy minimum, which is most likely the local energy minimum. And this is described by the analytical interaction function. So it's kind of deterministic in this sense. And you are assessing multiple docking poses by tries and errors using one algorithm or the other, and you are choosing the best one. In AI docking, it's completely different. First of all, you are not using physics-based energy functions. Instead, you are using pre-trained machine learning model, which emerges the optimal docking pose out of the noise, in the same way as, say, AI image generators work, where you give it a prompt, you start from the random noise, and the picture emerges. In the same way, the docking pose of your compound emerges from the noise. And it's based on the given input structure and the existing model weights, which are learned from the pre-existing data. This doesn't work like tries and errors. So it gives you the best pose in the understanding of this model right away. So you're not doing the random search. So this is a potential that this would be faster. And the model is trained on the existing data. So for example, if we are speaking about protein-ligand docking, it's trained on the data of the protein-ligand complexes, which are resolved by cryo-EM or X-ray. And potentially, this could be free from the limitations of the physics-based docking. It could be faster, it could be more deterministic, it could be more correct in terms of the chemistry of the poses which we get. What do we need to get this kind of fancy AI model? Well, we need the data. So we need to train the model on something before we can infer the poses of our own compounds. And we will limit ourselves in this talk to the protein-ligand docking, just to not to get it too long. And for protein-ligand docking, what you have the PDB data bank, where you have all the structures of all the proteins around, but only part of these structures actually contains the small molecule ligands. And only part of these ligands are annotated with activity or the binding affinity. So in a way, you have two major databases where you find the data which is useful for training AI docking models, which is PDB bind and binding mode databases. The first one, the PDB bind, have the structures which have the binding energy annotated. So it's either experimental binding energy or computed binding energies. And the binding mode is a database where you have the complexes, protein plus ligand, but not all of them have the binding affinity. So depending on which kind of model you are training, you can use both of them or one of them. When you will look at this data, you will immediately see that there is a number of problems in this data set. And the first problem is quite limited. So the overall number of structures when you have the protein with the ligand is about 55,000. It sounds like a lot, but if you will compare with the whole PDB, it's a very, very small fraction. And moreover, the number of complexes with measured affinities is less than 20,000. And the number of high-quality complexes with high-quality binding affinities is even less. It's about 10,000. And you probably know that when you train any kind of AI model, you have the situation garbage in, garbage out. So if your data is not good enough, your model would not be good enough. This is not the end of the story, because you only have about 20,000 ligands, small molecule ligands in these complexes. And only about 1,500 of these ligands are present in more than one protein. So you can imagine you have a molecule, it's crystallized with only one protein. You have no idea how the molecule binds to anything else. And of course, since you have one crystal, you have only one pose of this molecule. So you have no idea which alternative poses this molecule may have. Then the proteins themselves are also very unevenly distributed. So for example, 1,500 proteins correspond to 80% of all the ligands. And this is understandable because most of the ligands are found to families of proteins like kinases, GPCRs, transport proteins, ionic channels maybe. But for other kind of ligands, you have pretty much nothing. Then you have the protein families. And this is also very important because for each family you need some understanding where the molecules can bind. And only 100 protein families represent 16% of all the data. So if you will look at it all together, you will immediately see that this data set is first very limited and it's very skewed. So it's not evenly distributed. And it's kind of bad data set for machine learning and for AI techniques. So how can we overcome this lack of data? Because if you will train your model on the existing data from PDB, you will get something which is not very useful. The accuracy of this model would be very, very low. And there are two ways of addressing this problem. First way is to make your AI technique, the architecture of your AI model, very complicated. This is a way where authors of the AlphaFold are taken, for example. If you will look at the architecture of AlphaFold, this is one of the most complex AI models around in biology. It's insanely complex, and it's also very slow because of this, so it's very heavy. As I said, in docking, you have to be fast. So this is not the way you want to go. And in order to be fast, your architecture of AI model also should be fast. So you don't need to have like 2 billion of parameters, because it would take minutes and hours to infer one pose of the compound. So you need a lightweight model, and the way how to get the accuracy out of this lightweight model and to feed it with more data, to overwhelm the model with the data. And for this, the data augmentation techniques are handy. So what is data augmentation? You have your real-world data, and you are trying to make kind of synthetic data around it in order to feed it into the model. So in our case, what we did in our model, we took the statistical distributions of interaction in real protein ligand complexes, and we generated kind of artificial binding pockets around the ligands. The beauty of this technique is that actually you can take any ligand, not only the ligand which is found in PDB structures, but anything from chemical databases, and you can build a kind of fake binding pocket around this. Then you mix these artificial pockets to the real ones, and you train the model on this mixed data set. So the assumption here that we assume that all major non-bonded interactions are already present in the experimental data, so we can rely on this, but we don't see all the combinations of different interactions, and by doing this kind of artificial pockets, we are showing the models all possible combinations. Also, the augmented data teaches the model to recognize corner cases, some chemistry which is not present in the PDB, or some conformations which are very rarely occurring. So by doing this, you're making the model robust and kind of bulletproof, so that when the model sees this corner case, it will know what to do. So how it looks like? So we considered 13 different interactions, which are subdivided into several classes. You have hydrophobic interaction, you have hydrogen bonds, and you have number of other interactions. So here, for example, you can see features of the ligand itself and features of the protein binding pocket where this ligand belongs to. And you have different interactions like electrostatic interaction, hydrophobic interaction of different kind with different atoms, hydrogen bonds, amide pi interaction, cation pi interaction, and pi stacking. Of course, you can expand this list if you want and subdivide it even more. But if you will look at the statistics of the number of these interactions in the PDB, you can see that the most underrepresented one is halogen bond interactions, and you have less than 1,000 of such interactions, which is already kind of threshold. If you go below this, you cannot train your model. You don't have enough data. So this is a kind of natural number of classes of chemical interactions which you can work with. And after that, what we did, we computed the experimental distribution for each of these interactions and tried to achieve the same distribution when we are doing the artificial binding pockets. So for example, here you can see how it looks like for hydrophobic interactions. This is a hydrophobic for different pairs of atoms. For example, carbon or S with carbon or S, CS with halogen, CS with fluorine, and so on. As you can see, the correspondence is not ideal, but it's kind of decent. And this is enough for us, because if the trend is there, then the model will be good enough in discriminating these interactions. Here you can see what goes on for pi stacking and amide interactions. Again, the correspondence not ideal. For example, here it's kind of vice versa. But what is important is that it's located at the same region of the angles for the bonds, and this is the most important for us. And for aromatic rings, for example, the correspondence is kind of ideal. So it really depends on the interaction and the algorithm which you use to generate the pocket. In some cases, we see something funny. So for example, when we have the hydrogen bond and the acceptor is on the ligand and the donor is on the pocket, on the protein, this is experimental curve, this is what we get. So it's kind of not ideal, I would say. And it was kind of notoriously hard to optimize this. So we still don't know why. And we decided to go with this and see if it really works or not. And the spoiler, it works. So you should not be better than this. This is enough. So I will not stop on this. This is again for halogen pi and so on. So after that, after we get the algorithm which reproduces these interactions correctly, we can generate as many these fake pockets as we want. And after that, we can train the model. So how it looks like in our case, we generated, sorry, I will skip here. So we generated about 2 million of these pockets, in addition to about 55,000 of real pockets. And after that, we mixed everything together. Also important thing, when you teach your model to recognize these artificial pockets, you should show the model negative samples as well as positive samples. So the negative samples were prepared in such a way that the compound inside the pocket doesn't really correspond to the artificial pocket, and you need to have the balance between the number of positive and negative samples. All this is good, but we all know that proteins are not only complex but also dynamic. So the protein moves, the binding pose of your compound also changes as the protein moves, and right now the model is only aware about the static complexes. So how can you teach the model to recognize the dynamics of the protein? The answer is you can augment your model with data from MD simulations. This is tricky, because as I said, the number of protein ligand complexes is kind of small for machine learning, but it's kind of large for MD. So if you have 55,000 complexes, and it takes about 1 week to complete the MD simulation for one of them, you can count how many time you need. So we managed to do this for 17,000 protein ligand complexes, and this took about two months on the Google Cloud. We get the grant from Google for this, and the price of computer time for this was about 200,000 euro. And this is not enough, again, spoiler. So this is quite costly, but nevertheless, we were able to compute the MD trajectories for all these 17,000 protein ligand complexes with some limitations. First, we were unable to work with the membranes. So all the membrane proteins are simulated in water, which is kind of sucks, but we had to live with this. Then we have no proper complexes where you have multiple subunits in the protein. Again, it becomes too large to simulate in most of the cases. And since you are limited with your computer time, you also have kind of uneven simulation times. So you simulate most of the proteins for about 30 nanoseconds and some of them up to 100 nanoseconds. Typically, you need to run it for about microseconds. So you're like 2 orders of magnitude below what you want to achieve, but that's what we get right now. One important thing here, when you work with a protein ligand complexes, the ligands which are found in PDB are usually quite bad in terms of chemistry. So when you have the crystallization of the protein, you are crystallizing the protein with ligand. For protein, you understand the chemistry. For ligand, you don't understand chemistry that much. So when you go from the electronic density to the real conformation of your small molecule, you can get the chirality wrong, for example, or you can get the double bonds wrong, or things like this. And this becomes really painful if you are doing this kind of massive simulations. So we use a preset data set of PDB ligands, which is called MISATA data set, where all the ligands are already curated and have the charges assigned to them. Well, then we also use this data to augment the model. And what we get the RT-doc, our AI docking model, which is a model for ligand binding pose prediction. And this is important because we are predicting the pose, but we are not predicting the energy. The reason for this is that, as I said, the number of complexes where you have an energy, it's only about 20,000, which is not enough. But in order to predict the pose itself, the geometry, you have much more. We also include only the binding pocket, so we are not working with the whole protein. This is not a blind docking, this is a docking in the pocket. But by doing this, we are having less structural noise, and we also have much faster model. And by augmenting with this fake pocket and MD simulations, we are feeding the model with more data than anybody else right now. And we are also able to integrate the protein dynamic to some extent. And here's what we got at the end when we trained this model. We need some kind of benchmark for this, and there are several such benchmarks. One of them is called the Aztecs dataset. This is a dataset for assessing the docking models, which was created many years ago before the AI hype started. And usually it's considered that most of the conventional docking and modern AI docking model are performing well on this dataset. It's not particularly challenging. But as you can see, if you have the RT-doc, our model, and you have the conventional physics-based docking, like Vina, which is open source, or Gold, which is commercial program, from one hand, and some other AI docking techniques from the other hand, you see that our augmentation scheme is actually giving us an edge against both conventional and AI docking models. You can also notice that there are 2 kinds of bars here, the solid bars and the dashed bars. The difference is that the dashed bar is the molecules which are within 2 angstroms of root square deviation from the crystal structure we are comparing to. And the solid bar is not only within 2 angstroms of RMSD, but also the chemically correct pose in terms of the Postbusters valid metric. I will explain a little bit later what does it mean. The other dataset which we have is a Postbusters dataset, and this dataset is already designed, it's actually published last year, and it is designed to challenge the AI docking models. And again, spoiler, it doesn't challenge them anymore. So AI docking models are already okay with this dataset. So it includes multiple structure quality metrics in addition to the RMSD itself. And there are several versions of these datasets. The first one was made in 2023. The last one was published finally last year. And the funny thing is that actually all AI models started to compete on this data set like 1.5 years ago. And up to now in 2025, most of the models are already overfitted. So the models are getting like a 99% accuracy on the postbusters data set, and it doesn't make sense to look at this. In our case, we are not training the model in such a way that it sees anything in this data set. So it's kind of fair comparison, and there is no overfitting. That's why you will not see for our models numbers like 99%, because this is fair. When you will see 99% for any kind of AI model, this is either overfitting or something is wrong. So again, we compared our RT-doc with multiple different techniques. And as you can see, we also get a kind of progress from one version to the other. And in the latest version, we are getting about 78%. And this is on par with the AlphaFold. So the AlphaFold is not a docking model. The AlphaFold is a co-folding model, but it's able to predict the binding of the ligand if you give it a ligand and you're doing co-folding with the ligand. It's very slow, but it's very accurate. And actually, when we see that we are on par with the AlphaFold, it's kind of convincing for us that we are really performing well. Coming back to this postbuster matrix, as you can see, there is kind of gap between the RMSD only and RMSD with the postbusters valid matrix of chemical correctness. And the situation with the conventional docking is a little bit different. There is almost no gap. So the conventional docking is giving you chemically correct structures. And AI docking giving you the structures which are kind of fine in terms of RMSD of individual atoms, but not as good in terms of chemical correctness. And this gap is kind of have to be minimized if you want the chemical correctness as your goal. And with RT-doc, you have multiple parameters to tweak, and you can either prioritize the absolute best RMSD, or you can prioritize the difference between these RMSD and postbusters. And as you can see, with optimal set of parameters, we are at the same range as conventional docking, while other AI techniques doesn't reach this, as you can see here. Coming closer to this chemically correctness matrix, what is there? So first of all, you have 3 classes of chemically correctness matrix. You have the chemical validity, you have intramolecular validity, and intermolecular validity. For chemical validity, it means that you should get the double bond stereochemistry correct. If it is cis, it should be cis and not trans. You should get the tetrahedral chirality correctly. You can get the bond lengths and bond order correctly. You can get, of course, the molecular formula, sanitization, and your file have to be loaded correctly. This is kind of for granted. And as you can see, if you will compare our technique with other techniques, so I somehow don't have the legend here. I don't know why. So, okay, it's here. It's on the bottom. It should be somewhere here. I don't know what's going on with the slides, but anyway. So you have the RT-doc here in purple. You have the AlphaFold, which is blue, and you have the older AI docking model, DiffDoc, in gray. And you can see that actually this is a percentage of correct predictions. And you see that most of these chemical validity metrics are close to 100%, except the tetrahedral chirality. And surprisingly, the AlphaFold does worse here. So the AlphaFold doesn't care about tetrahedral chirality. We don't know why. But RT-doc actually scores 100% here. Then we are going to intramolecular validity. So which means that you should have no internal sterical clashes. The molecule should not clash with itself. You should have planar geometry correctly of the double bonds and aromatic rings. So aromatic rings should be planar and not like this. Then you need to have the correct bond lengths and correct bond angles. And also what is called the energy ratio. It's a kind of strained geometry metric. So if your geometry is relaxed, it should be smaller. If your geometry is strained, like mechanically, then you have the larger energy ratio. And as you can see, again, all of them are close to 100%, except these sterical clashes and energy ratio. And again, we are doing quite well relative to other techniques. Then we are coming to the most challenging part, and this is intermolecular validity. When you have your molecule and you have the receptor, and you're looking at the minimal protein-protein ligand distance, for example, which means if this distance is too small, then you are clashing into the protein. Then you have the minimal distance to the organic cofactors. If your protein contain any kind of organic cofactor, like ATP, for example, or anything else, then you can also clash into these accidentally. And you can also have inorganic cofactors, like ions or metal atoms. You can also clash into these. Then you may have the volume overlap with the protein, and you can have the volume overlap with cofactors of different kind. And here the situation is much worse, as you can see. Even the AlphaFold doesn't score 100% for all of these. So for example, AlphaFold have some bumps, spherical bumps between the ligand and the protein, and also for the cofactors. But if you will look at the previous generation of the I-docking model, the DiffDock, it really sucks here. So the metrics are really bad, especially for the clashes. For RT-dock, it's much better, as you can see, but it's still not 100%. So there's still room of improvement here. Next thing which we need to consider is the speed. As I said multiple times already, the docking have to be fast. And if you will take AlphaFold, which is kind of the best AI model out there, as I said, it's co-folding model, and for predicting one protein ligand complex, it takes about 15 minutes. It depends on the hardware. If you're working with some industry-grade GPU, it could be like 5 minutes, not 15, but nevertheless, it's quite slow. On the same hardware, if you will take the open source docking program Vina, you will get about 3 minutes. If you will get the commercial docking program Gold, you will get about 1.5 minutes, and so on. And for AI docking, there are different kinds of AI docking in blue. You can see it's kind of order of magnitude faster. And for RT-dock, we are about 1.5 seconds. If you will compare with AlphaFold, it's 600 times faster. If you will compare it with, let's say, Glide, which is kind of industry standard in the Schrödinger suite, which every pharma company is using nowadays, they are kind of order of magnitude faster. So what it gives us? It gives us an ability to work with very high throughput, so we can work with millions of compounds, or we can dock into multiple conformations of the same protein, or let's say to several mutant proteins, or several isoforms of the same proteins, because of this speed. And with conventional docking, you cannot achieve this. So if you get kind of detailed comparison with what you get the state-of-the-art commercial docking program, which is Glide now, and our closest competitor, which is Unimo, it was our closest competitor last year. This year they actually no more. But this is kind of a little bit outdated comparison. So you can see how you compare. You're comparing with different cutoffs of MSD. So you have your ground truth, which is your crystal, and you are trying to be within 1.5 angstrom MSD, 2 angstrom, and so on up to 5 angstrom. And you're comparing percentage of correct predictions. Of course, when you're relaxing your criteria, you're becoming more and more accurate. For 5 angstrom MSD, almost all the poses are within the accuracy range. But what is important here, how you go from the lower values to the upper values. What is the trend? If you will look at the RT-dock and Glide, you see that accuracy increases when you increase the cutoff. With Unimo, you have kind of constant. So this is not optimal. For absolute values of these postbuster valid metrics, we have always comparable metrics for RT-dock and Glide. For Unimo, you are getting low. So you see it's always below. So to make the story short, we are kind of on par with Glide in terms of accuracy, but we are much faster. And we are comparing with Unimo, our competitor. We are much better in terms of chemical correctness. So, conclusions. First of all, AI docking is progressing very fast, and actually each month you are getting something new and more exciting. And this is already kind of viable alternative to commercial conventional protein ligand docking with high accuracy in terms of the poses, RMSD, with comparable chemical correctness and much faster, like an order of magnitude faster. But there are some remaining challenges, like limited real-world validation, because people are kind of hesitant to use it right now. It's also available, it's not also as available as conventional docking, because for conventional docking you have just an executable program which you can run on your own computer. With AI docking it's not as simple. You have some Docker containers, you need powerful GPUs and so on. And we still have some questions about generalizability to some exotic molecular species. But nevertheless, the AI docking is here. It's most likely the next decade will be the decade when we will see substitution of conventional docking with AI docking, and maybe substitution of humans by AI models. And thank you for your attention.
So thank you for the lecture. And now, if there are any questions. And I would have the first one. You were speaking about that the problem with the conventional docking is that you have multiple possible poses that have similar energies.
Yep.
My problem with molecular docking is that you don't have an error bar.
Yes.
Is it possible to get the error bar out of the AI docking?
Yes and no, and this is a very good question, because error bars is a pain, also for conventional docking and for AI docking, and in AI docking it's even more a pain, because there are two types of AI docking. One where you predict the energy, and one where you predict the pose without energy. So for RT-dock, you only predict the pose. So on top of this, you have to have another model which will take your pose and will assign some kind of score. This is not included, so it's not like batteries included. With this second model, you can get kind of error bar, because what you can do, you can generate multiple poses and you can compute the energy, and after that you get the error bar, but after that you are losing the speed. And this is the same problem with conventional docking. For conventional docking, it's kind of easier because you are getting multiple poses already out of the docking run. Here you have to run several times.
Questions? Klidně i otázky, já to určitě tak přeložím.
So in these situations, I always say either everything is clear or nothing is understandable.
So, I would have a question concerning the business. How do you sell it?
Quite nicely. So we are not selling the model itself, so it's kind of integrated into the whole workflow which the company is doing. But this is one of the selling points. And this is a selling point not only because it's great in terms of performance, but because it's kind of advertisement magnet. When you show the people this and you say, hey, see, we are on par with AlphaFold, but 600 times faster, it's kind of wow factor. And this is really selling itself well.
Okay. But I suppose that you have NDAs in order to say what systems are you working on?
Yeah. Yeah, so I can say that we are working with pretty much anything, so different classes of proteins. We have kind of public statistics which kind of proteins we are working with. It's like 25% kinases, 25% GPCRs, like 20% ionic channels, and anything else. And this is pretty much the same statistics as any pharma company has, so it's the most common targets out there.
Still no questions? Not even the basic one. What is it for?
what kind of business it would use this technology? Like, if you sell it to them, not the engine itself or the AI itself, but what?
Even the basic one. What is it for?
Yeah, it's somewhere from there. Yeah, so the consumers of...
What kind of business it would use this technology? Like, if you sell it to them, not the engine itself.
What's going on? Anybody knows? Okay, so I will try to answer the question. I hope it will not go like this again. So the customers are typically the pharma companies or biotech companies or CROs which are doing actually screenings for the pharma companies. So it's B2B. We are selling this to other companies which we are not selling to the customers. But of course, we can also propose this for, let's say, universities. We are not doing it right now. Maybe, Carol, we can think about this, but we are not doing it right now.
As you said, you like to cut down on the time that it takes to predict the poses. So which one do you prioritize right now? Is it the time or is it the quality? Like,
so we are trying to prioritize both because you see, if you want to screen like millions of chemical compounds against the protein, it's typically done in several stages. You are doing kind of initial screening just to find the candidates, and after that you are doing the secondary screening with better, more accurate parameters. So it's useful to have both. Very fast but not so accurate, and very accurate but not so fast. And by changing the parameters, you can achieve this.
and have you considered working with the other AI companies to sort of put together all your strengths and raise your weaknesses?
Well, there is a lot of competition in the field, I would say, but of course we are working with other companies. I cannot disclose this, unfortunately, but mostly we are working with experimental companies who are validating what we are doing. In terms of AI companies, the landscape is quite competitive, I would say. So it's not so easy to collaborate with somebody. It's much easier to collaborate with academic institutions, with scientists.
Thank you. As you are showing the AlphaFold latest, I do recall that when I'm using AlphaFold on AlphaFold server, there is just the limited amount of the molecules. So is there a way how to run any other molecule as well?
So this one is actually the results from the AlphaFold article itself. So we were not doing this ourselves. But now you can, because now you have the open source AlphaFold 3 model, which is Boltz-1 and some others. By the time when we were doing these benchmarks, there was none of this. So we just use the data from the paper. And now when you will do this with AlphaFold 3 open source, you are getting the number which is lower than this, which is interesting. So you cannot really reproduce what they did when they released the AlphaFold, and we don't know why. But it's not possible to reproduce.
Some experimental some expert knowledge.
Some expert knowledge, yeah. There are also other explanations which I would not tell, but yeah.
Let's stay at the expert knowledge.
Yeah. Let's go it like this.
Yes. Any other question? Okay, so I think let's conclude the session. So thank you all for coming. Thank you for the lecture.
Thank you for inviting me.
And if I recall well, the next will be in 2 weeks, and it will be by Jan Wilím from Enantis company, who will be speaking about the producing of the proteins, engineered proteins for the industry and for the healthcare. So See you in 2 weeks.